Your vocal exercise.
How many people right now? How many people right now?
I don't know. It's all good. Pretend that we're just talking amongst friends.
0 people. Nobody's watching. It's just.
Yeah, it's much easier when you imagine 0 people.
Yeah, 0 people. No chance of sharing up.
Okay, we got 30 seconds. Yeah. Not right now, but like we're starting on here, right? Yeah. And we're gonna move it over to them. Just cue me when you want me to. Okay.
Hi, everyone. Welcome back to another episode of Dynamo Livestream. This particular livestream is really special because we're actually hosting this office hours at our very first customer's office. And as you saw, it is base 10. And so before we start, let's do a round of introduction. Bryce, would you like to go first?
Yeah, well, yeah. Thanks so much for coming up here. We're super excited to be on. I'm Bryce. I'm a model performance engineer at base 10.
I'm Michael. I work on also the model performance team at base 10. We're pretty early adopting Dynamo and excited to be hosted here tonight.
Awesome. And you probably saw me before, but my name is Harry, and I'm a product person for Dynamo. And John?
I'm John. I'm an engineer on the Dynamo team, primarily focusing on KV Block Manager.
Yeah. So we're extremely lucky to be here. So thank you again for inviting us. Maybe we'll just start with talking about base 10, because if you actually live in San Francisco or Bay Area, it's really hard to miss. You see them everywhere. But for the viewers who don't know what base 10 does, could you give us a bit of a description?
Yeah. So we're a model inference provider. We help customers serve AI models in like a scalable, performant, and cost-effective way. That involves working with different runtimes, working with different clouds, and combining like performance optimization features together to help them serve AI models.
Yeah, and it was incredible to kind of watch your progress, say on OpenRouter, because we know that you guys already wrote a blog about it, but you guys are topping the charts on OpenRouter, GPT-OSS, both for throughput and latency, and then also even before GPT-OSS, you guys also did the same thing with DeepSeek V3. So that was like super impressive. So maybe you could talk a little bit more about how you guys were able to achieve such a great performance.
It's not only time to first token, it's also time to like pushing this out. I think from GPT-OSS, it was like we said 24 hours. It was a bit faster, and there's a lot of work that goes into like bringing up a new model, bringing up in terms of OpenAI. I think I remember like Bryce was sitting there and we pushed into the OpenAI repo back because like the full call parser was not compiling from their side. There's more Rust project, but if you work a lot with Rust and Dynamo and Pio 3 bindings, you're pretty fast actually getting that out. And there's a lot of things to consider, like lots of if you host this for everybody and you're like the first out, there's a ton of like OpenRouter pushes a ton of tokens on you. People request for it. Slack is just exploding from customers that want this, for example, GPT-OSS model, and they like text, and they're all combining their workloads. So there's a lot of things that helped us with like adopting Dynamo early was quite helpful in kind of helping with this. And I think there's also now an option to do things beyond runtime. So we have quite like a lot of improvements on stability for KV routing too. And I think Dynamo is like currently, we think, the best framework to build upon for this.
Oh, thank you so much. And we were actually really surprised because I know that you guys had a Business Insider article talking about how you wanted to switch quickly to the new and shiny thing that is going to support the best performance. But also at the same time, I think you guys are the only one customer who is running Dynamo currently in production that decided to take the 0.1 codes that we released at GTC. And so could you share a little bit more about your experience with working with Dynamo, and what are some of the good bits and what are some of the things that you had to improve on your own? So, yeah.
Obviously, like we were adopting it quite early on, and there were things to do like inside of the core where it obviously there's a lot of requests. There's back then it was like a bit earlier, and there was like smaller optimizations to do. Like we also host things like Llama 4 on it with like 1 million plus context length, and for this context length, you find like any exposure if there's like any deficiencies of like, for example, putting request streams on nets and maxing out really the context length. There's a lot of unexpected things happening, and you had to fix them. But also some of them, these changes also contributed back to Dynamo. I think it's pretty simple as a setup of a project, and I think big step up from like previous runtimes, like starting out from like Triton server. Now you can like build this thing pretty easily. You can contribute back. There's a really active community, and I think this was an insane cool thing to work on.
Yeah, I mean, I think for us, it's that it allows us to like could put all of our performance features on top of it, and it gives us this great starting point that does a lot of things really well. Like it having support for different like serving backends and having that as a modular component, like allowing us to implement any like business logic, whether that's billing related for customers, whether it's custom, output or sampling logic, whether it's tool call parsing. And yeah, I think those have been really nice things about it to build on top of.
I see. Yeah, and we definitely paid much more attention to make sure that it's easy to contribute to the project. And so we had to make sure that before Triton Inference Server, for example, we didn't really have a public CI set up. And so this time when we released Dynamo, we made sure that that particular feature is there so that it's easier to contribute. But definitely, I remember seeing some of the PRs that are being pushed by Baseden about billing too. So that was interesting to see. But yeah, maybe we can talk a little bit more about, say, GPT-OSS, for example, because one thing that was very impressive was you guys were able to support GPT-OSS right when it came out on the day 0. And it's really hard to do that. So I know you guys already worked with, you guys are working with OpenAI, but so that other folks in this industry as well. And so maybe if I were to ask you a question, can you share the secret sauce without actually sharing the secret sauce? Is that a possibility? Like, what are some of the things that you guys did something differently that you think that is giving you guys the best performance at this point?
Yeah, well, so we put out a blog about it, which I encourage anyone to go read, but we can definitely go into like some of the performance optimizations that we looked at and how we like ended up with our final configuration. Yeah, I think whenever a new model drops, you're always trying to understand like what settings are going to be best for the customer, but also for the use case. And we did something similar for GPT-OSS. So we serve it with TRTLM, which is one of the great things, the integration with TRTLM and Dynamo. We tested various configurations of expert parallelism and tensor parallelism, and we found that for the like latency target that we were looking at, we went more heavily towards tensor parallelism for the deployment. And then I think another interesting like decision we made was, so TRTLM has multiple MOE, backends. And I think the default is the Cutlass one. And we found that the best configuration for it was to use the TRTLM MOE backend, which uses like the TRTLM gen auto-generated kernels. So those are that was kind of our starting point that we had out on day one, and then we've continued to look into all of the other techniques we can put on. How do we scale workers? But I think those are the main things, and yeah, the NVIDIA also talked about some of those optimizations in TRTLM too.
Yeah, and we also know that John has been working on getting the best performance out of GPT-OSS, namely for NVL72. So could you share your experience with it as well?
Yeah. So I guess starting, I guess initially, in short, this initiative was to take Dynamo with GPT-OSS on NVL72 and see how many tokens per second we can get. Currently, we're up to 1.5 million tokens per second across a full NVL72, and that required a couple key performance optimizations. The first one, really big one, was that we weren't doing incremental detokenization. So when we received some new streaming chunk, we added it to our list of output tokens, and then detokenized the entire sequence. And that's, especially for longer ISLs, that introduces an enormous CPU bottleneck. So switching to that significantly reduced CPU overhead and queuing in our front end. The second big optimization was actually dealing with some subtle issues to do with thread starvation for the threads, or I guess for the async tasks responsible for networking. In our current setup for Dynamo, we have one async task per request. If we're serving at concurrency of, say, like 40,000, for example, that's a lot of async tasks. So we have tens of thousands of async tasks that are doing some pretty compute heavy stuff, things like pre and post processing. And at the same time, we have a very small number of async tasks responsible for networking. And this, obviously not great. I mean, the tasks responsible for networking are incredibly performance critical. So what we were seeing is that there were, at some points, there were thousands of requests that had been fully pre-processed, but we're just waiting to be sent over the network. And with that's enabled us to get up to the full 1.5 million.
It's pretty impressive. So,
big number.
Yeah. Can you say that again? Because you kind of mentioned it in passing almost. So I think, what's the performance that you're actually getting with GPT-OSS on NVL72?
Yeah, we can get 1.5 million tokens per second across a full NVL72 rack.
Super impressive. Is that script going to be available soon, or?
I don't see why not.
Okay.
Yeah, I mean, currently the benchmarking setup is a bit bespoke, because I guess the big problem with that is there's not really any benchmarking tool that can handle, say, like concurrency like 50,000 for example. So what the setup that I currently use to benchmark it is I grab another dozen GB200 nodes, and across each of those nodes I run effectively a reduced concurrency benchmark. So let's say I'm targeting concurrency like 50K. On each of those 10 nodes, I run a scaled down benchmark with I guess number of requests and total concurrency scaled down by a factor of 10. I use some admittedly ugly MPI hacks to make sure all those 10 benchmarks all start at the exact same time. Because I mean, otherwise, like if you have some benchmarks starting before others, I mean, that's your results are going to start to diverge a lot. And with that, I've actually found pretty reasonable results. Metrics like TTFT and total throughput for each of those like 10 nodes, for example, only differs by around a couple percent. It's certainly not ideal for sure, but it has I found it has worked pretty well for extremely, I guess, massive scale benchmarking.
Wow, that's something that I didn't even know about. So it's very interesting to hear. But yeah, it'd be awesome to get the script available so that we can make sure that all the developers have access to it. So looking forward to seeing it. But maybe we can also talk about the other kind of a beast of a model, which is DeepSeek V3/R1. And so we also know that you guys had an amazing performance on OpenRouter with this model too. And so just wanted to kind of also ask you about your experience of deploying this model. What are some of the things that was really challenging? Obviously, he talked about scaling. Scaling is obviously a big challenge, but just wanted to hear your thoughts.
I would say, yeah, so I think, yeah, one of the interesting things about DeepSeek and R1 is like, they're so enduring in terms of like people's demand for them. And when you're talking about scale, I would say there's almost always like, people want more tokens. They want higher rate limits on it. It gets a lot of traffic. And yeah, I think that was one of the first few models that we supported in our model APIs product. Yeah, it was a similar process for DeepSeek. At the time, so for people who maybe are familiar with TRTLM and they worked with it when it used to be the engine flow. I think right around, it was one of the first models that was supported only in TRTLM torch flow and not in engine flow. So the engine flow required you to like build a model ahead of time. You have to compile it for a certain GPU, whereas torch flow, more similar to, kind of you look at the code, you could be looking at torch modeling code, and it doesn't have this ahead of time compilation step while still having like, best in class performance. And so that was the first model that we were serving using TorchFlow. And so, yeah, similar optimization process where we kind of compared what the throughput and latency profile we wanted, what like backends and flags that TRTLM had available. And because it's been around for so long, like iteratively improved upon. I would say the one interesting thing with DeepSeek V3, because they have the MTP heads built into it, that gave us another starting point for speeding up the model with speculation, which we see is like hugely important to the like perceived per user throughput for the model.
Great. Could you share how much performance benefit that you got from the multi-token prediction? Was it pretty massive?
I think without multi-token prediction, like it's like definitely under 100, right?
Yeah, I'd say like you can if you look at like there's also public benchmarks of saying what Tensor TLM can do. There's I think we could verify basically the exact same numbers if you have this like running this like isolated benchmark. You get like 90 to 100 tokens a second in the vanilla configuration. For example, on a B200 node, like 8 times B200, but then you can gear it up and add MTP. You can add CUDA graphs on top of it. You can add like FP8 KV cache. You can, this is pretty interesting. You can get up to like 250-ish tokens a second in most scenarios in prod. And I think the interesting thing is also to maintain it is if you have like outside of benchmarks, also real like workloads running on it. There's like people requesting short context, long context. You have to have the auto scaling in place. Customers requesting things like structured output on it. Then you have to modify the like X grammar or like structured backend to actually work with structured output while you predict next more than one token ahead of time. So that's pretty challenging, actually. Otherwise, you can't offer, for example, structured outputs. But yet we do that. And if you would You could alternate and bring up 2 deployments in 2 different whatever CUDA graphs, but you'd go pretty fast out of performance, and your like performance publicly would drop quite a bit, would reflect this kind of setup. So I think that's one of the secret sauces. I'd say.
Okay. Secret sauce without sharing the secret sauce. Okay.
So
That's great.
A lot of different workloads that you have to be good at to reflect good in these benchmarks.
I'd be kind of curious, was there any work done for like the NVL72 for DeepSeek v3 that transferred to your work, John, when you were trying to optimize GPT-OSS?
At least as far as I know, the runs we've done with GPT-OSS were the first time, at least internally, that we've tried to push Dynamo that far. So it was quite interesting because that was just completely uncharted territory for us at that point. Certainly ironed out a lot of performance issues in that process, which of course is good. Or bad, I guess, depending on your perspective. But yeah, I guess the optimizations we currently have in the main branch of Dynamo based on that NVL72 work can benefit practically any model in a high throughput scenario.
It's exciting. Yeah.
Okay. So obviously one of the issues is scaling, but I think you guys were asking about a different type of challenge that you're facing, namely how do you manage KV cache effectively? And so could you share what your challenges currently are?
I think on the high level, as I mentioned previously, like KV routing works insanely good in Dynamo. It has this option of like basically if people worked with this KV routing, you like have a notion of where can I find KV cache and route it to the right place. Now you're stuck with the challenge of like, how can I have more KV cache? How can I potentially say, okay, these requests are more important than others, and I want to retain some of them. This is going to be a reoccurring user, for example, is stuck in the chat. There's requests to like have like some kind of priorities of that. And I think the overall topic of like KV cache offloading, having like massive throughput on like basically, these are like pretty exciting things beyond like, for example, the KV routing. And
and good news is that we invited John for that exact reason, because we just had our KV block manager functioning with VLM, and also what we call, maybe not use the nomenclature, but being able to offload from GPU memory to host memory, and then also onto local disk. We are also trying to enable this for remote storage as well. But John has a quick presentation that he's prepared.
Okay. Let's see. Oh, and they can see my screen, right? Okay, cool. I'll just do a quick presentation on what we call a Dynamo KV block manager. I guess to start, sort of a high level overview. KV block manager is in essence a solution for advanced KV cache management. I guess a bit of a primer here. There's nomenclature we use for different cache levels. We have 4 different cache levels. We have G1 for device memory, G2 for host, G3 for local SSD, and then G4 for remote like networked SSDs. Our current scope of functionality that we support in KV block manager is offloading and onboarding KV cache between G1, of course, and then G2 and G3. Some more, I guess, longer term initiatives that are either that we're either considering or I guess are sort of underway are of course offloading to G4, as well as a couple more advanced workflows. So for example, a heavily optimized implementation of PD disaggregation. One, I guess, one strategy we're exploring for that is, instead of transferring KV cache directly from pre-filled GPU memory to our decode GPU memory, we instead transfer from pre-filled GPU memory to a host buffer on the decode worker. And I guess the reason why that that's interesting, I guess, is for, say you have like some like massive prefill on your prefill worker. The time it takes to compute that prefill, as well as the time it takes to transfer that KV cache, is going to be very non-trivial. If you just go immediately allocate your KV cache blocks on your decode worker right away, all those KV cache blocks are just going to be sitting idle. Not I guess useless per se, but not being involved in any like useful work. So we can instead transfer it through a host buffer on the decode worker. So we can say like, okay, after X% of layers have completed the transfer, then we can go allocate our KV cache blocks on GPU and begin transferring from host to device on the decode worker. So that's one of the, I guess, future paths that KVBM may support. Another one is KV cache sharing. So this could be super useful for something like KV aware routing. So for example, say you're routing between two different tier TLM workers, let's say, and your router, it sees that you get some request. You see that like, okay, there's a really big cache hit on worker 0, but at the same time, worker 0 is like really overloaded with requests. And in the meantime, worker 1 is underutilized. The, I guess, optimal approach for how you'd want to serve that request would be to take your KV cache on worker 0, transfer it to worker 1, and then perform the remainder of the prefill, as well as all the decode steps on worker 1. And that's, I guess, optimizations like that require a very deep integration with Dynamo, especially as it pertains to KV routing. We need the KV router needs some separate, I guess, communication path, I guess you could say, with the workers to say like, hey, you need to go transfer this KV cache to this other worker, and that's, I guess, not really possible unless you have a full like end-to-end integration via Dynamo. And I guess in terms of integration point, I mean, a lot of the features I just mentioned are not simple, to say the least. So we need some sort of very clean, elegant way, and framework agnostic way to implement these features. Because I mean, if we have a separate implementation of this for TRTLM and a separate implementation for VLM and another one for SGLang, I mean, that's not practical, right?
Mm-hmm.
So the integration point that we use is what's called a KV cache connector API. So this KV connector API, it's effectively a minimal interface to be able to influence the KV cache manager on each of the workers. So we can influence the KV cache, influence the actual execution of the forward path itself. And there's really, I guess, there's really two sides of this interface. So there's a scheduler side, and this scheduler side of the interface, just a single instance of it runs. It's responsible for scheduling and orchestration. So it for example is responsible for telling the KV cache manager like, hey, I can load X number of new tokens from some external KV store that I have, or telling the KV cache manager like, hey, we have this request is finished, but don't deallocate these blocks yet because we're still using them for, say, like transferring them to a decode worker, for example. So that's the scheduler side. And then the sort of counterpart is the worker side interface. And the worker side is responsible for actually performing the transfers. So it's responsible for listening to the scheduler side interface, performing transfers, and reporting on the completion of whatever transfers commanded to it by the scheduler. And for this worker side interface, we run one instance of it for each GPU rank. So for example, if you're running TRTLM with TP4, let's say, you would have a single instance of this scheduler interface, and then 4 instances of that worker interface. And this sort of KV connector interface, it already exists in VLM, and there's an undergoing initiative to also port that directly port this over to TRTLM. And the reason I guess we're just doing a direct port of it, at least initially, is I guess simplicity would be the biggest thing. Longer term, we may want to put our own sort of twist on the TRTLM implementation. But at least for the time being, just having a common interface allows us to reuse practically all of our code between our VLM and TRTLM integrations. So in terms of what this integration actually looks like, I know this block diagram is a bit freaky, but I'll sort of break it down here. So we have in the middle, we have the KV connector interface itself. Actually, I'll show you guys. There we go. Yeah. So on the so we have the single instance of our scheduler interface, and then I guess n instances of the worker interface. At least currently, we I guess directly porting this interface into TRTLM is, I guess, it introduces a couple challenges. The biggest one being how we set up our parallelism. Because in VLM, at least in V1, there's a dedicated scheduler process, and that runs the scheduler, of course, the KV cache manager, and then there's separate processes for each of our GPU ranks. In TRTLM, the setup is a little bit different, where we don't have any sort of dedicated scheduler process. We have, I guess, one process per GPU rank. But each of those processes has its own scheduler, has its own KV cache manager, etc. So to I guess deal with this, we as arbitrarily decide rank 0 is the rank that we run our scheduler side interface on, and then we use some of the existing MPI logic in TRTLM to broadcast the results of the calls to the schedule side interface on rank 0 to all the other ranks. Because for example, we call into the scheduler interface. That interface tells us we can load, say, like 32 tokens from external KV cache stores. All of the KV cache managers on all of our GPU ranks need to have that information. Otherwise they're going to get out of sync, and that would be very bad. So yeah, I guess we sort of co-locate the scheduler side interface with the worker on rank 0. And then I guess that brings us to the KVBM side of this this diagram on the right, where these scheduler and worker side interfaces influence some internal state of the KV block manager. And that hooks into our transfer engine, which is actually performing all of our transfers between G1, G2, and G3, and I guess include G4 in there as well. Just for it's sort of more like future looking. But yeah, I guess beyond that, our I guess current strategy, I guess, for transferring blocks is, I guess, a bit different based on whether we're going from G1 to G2 or G2 to G3.
So it's like, so walk me through how this is, like when a new request comes in, you tokenize it, you figured out, hey, these are like some kind of blocks that I'd like to have, and the scheduler is going to ask like what I'd like to have these kind of blocks. It's like and it interfaces with the KVBM there and asks on the like schedule on rank 0, like are these blocks around, or how's it work at this moment?
Yeah, so all the pre-processing is completely unchanged. Just handled by the framework itself. When we go and first add that sequence to add that request to our KV cache manager, it goes and does all of its own processing, sees what blocks it can match against that already exist in GPU memory, and then it goes and calls into the scheduler side interface of the connector API. It says, okay, here's my request. I have this many tokens already resident in GPU. Asks, okay, how many with this info, how many more tokens can be loaded from external KV cache? For something like disag, for example, if we were running this connector interface on a decode worker, it would just return the entire length of the sequence, because its external KV store is just the prefill worker. So that's, I guess, the really nice thing about this sort of approach, where like functionally transferring blocks from say like host memory into GPU it's functionally equivalent to transferring blocks from a prefill worker to a decode worker. I mean, ultimately, the framework and the KV cache manager shouldn't care where these blocks are actually coming from. Just that they're just that they now exist in GPU memory. So yeah, I guess that's the I guess that's a really nice thing about this connector API approach. I guess one more thing to note from the in terms of our offloading strategy, every block that gets computed on GPU, we just eagerly transfer that to CPU memory, and from there we have to be from CPU memory to SSD. We have to be much more selective of what we offload. Just since, I mean, our SSD write speed is very scarce. Our current heuristic just looks at how many times a block gets evicted from host memory, and because I mean the thinking goes, if you see that a block gets evicted a bunch from host memory, our, I guess, like working set of KV cache blocks is too big to fit on our device memory and CPU memory, which indicates that you may want to offload to also transfer that block to SSD. Yeah, so I guess that sort of summarizes the integration we have. I guess for a quick little demo of this functionality, so I have VLM started up with our connector API. The command that gets used, just roll way up here. We just specify our KV transfer config, where we say, okay, take this module and import. This is the name of our scheduler class, and this is the name of our worker class. Then VLM is just able to automatically go and import that. I guess a couple more important things to note about this is, at least just for this demo, running with an extremely small GPU cache size of only 8 blocks. The reason I'm doing that is just because it's much easier to trigger the block, the trigger, I guess, onboarding of blocks from host to host to GPU. So I have just a little sample request here. So I can go and send this request. And I guess as expected, since I just started this up, there's no cache hit on host memory. But as soon as this request was computed, in the background, we went and transferred these blocks to CPU memory. So now I can go and clear out the KV cache in GPU memory, and then can send the same request a second time. And when I do that, we can go into the logs in here and see that we logged that we've transferred 4 KV cache blocks from host memory into the GPU. Yeah, so I guess that's sort of a I guess minimal example of functionality. In I guess in a real like production deployment of this, there would of course be a much bigger GPU cache size, which I guess means that you have to run for quite a bit longer. Even before there's even the pot getting in host memory or an SSD. But beyond that, this is it's beyond that caveat, I guess, with this little demo. That's sort of the, I guess, end-to-end flow of sending a request, offloading our blocks, and then sending another request that has a cache hit to go and onboard those blocks.
And because we're a bit short on time, I don't think that you showed the last slide with the result. Is that something that you can show?
Yeah, so there we go. Yeah, so in terms of performance for this, it's, I guess, as results here are, I guess, as expected, where a red line is just a baseline running with VLM. So no caching on either GPU memory or host or SSD, and as expected, the our TTFT scales roughly linearly, except for this point at 16 queries per second. I think that's, I assume that's just some benchmarking anomaly. So we can then go with this orange line, where we just enable the connector. So we get cache hits on host and SSD, but no cache hits on GPU. And we can see that has a pretty great speed up as is. And then of course we can go even further, enable also cache hits on GPU memory, and that, I guess, also as expected has a further improvement in TTFT.
Can you say verbally, because it's not labeled on the graph, like how much performance gain you're getting?
Yeah, I mean, at least for low concurrency, for example, we see up to, say, I mean, just eyeballing this, the delta between the red and green lines, I'd say maybe 80% reduction in TTFT.
Yeah, that's massive.
Yeah, that's exciting. Do you see any way that, how do you envision like users of Dynamo extending it possibly?
Yeah, I guess there's sort of a couple paths there. One of the big ones would be influencing what makes it from GPU memory to host memory, because currently we just try to offload absolutely everything to host memory. And if you have some really like low value request, you know that you're never going to get a cache hit on this again. It's just like some one-off request. Then using all that bandwidth to transfer to host memory is a waste, of course. So there's certainly opportunities for customization there in terms of I guess the specifics of what we offload. There's also a lot of possibilities moving forward for more, I guess, explicit prompt caching. So you have I guess the sort of flip side of the example I just gave, where you have some request and you know, like for certain, that you're going to get like a cache hit within some amount of time. A potential optimization that you could do there is still take those blocks, offload them to host memory, and then a bit before you believe that you're going to get a cache hit, you can transfer them back. You can sort of prefetch them back into GPU memory. So that's certainly another really, I guess, interesting avenue of exploration and optimizations there.
Super cool.
Awesome. I think we should take some questions from the audience. And so, John, I don't know if you already have it set up on your laptop, but
I've never used this streaming software before.
Yes, there is a question from Gorday. So Gorday is asking, what is the best way to organize LLM ops? Will Dynamo and TensorFlow LLM be sufficient, or are there any other components that could be added?
The best way to organize.
LMM ops.
Like LLM ops meaning like the operation of like running language models like in production for.
I think that's
User?
what he means, end to end probably. So
Yeah, I think that would get you pretty far. I think what you can add on top of it is like that's your starting point, and then like there's all of the like performance improvements, whether that's coming from custom kernels, whether it's coming from custom speculation methods, and really like use case specific optimizations that you can add on top of it. I don't know, Michael,
I think there's
yeah.
a lot of options, a lot of things to extend. We talked about different backends
Right.
for different model. For some new model, there's like GPT OSS coming out with a completely different attention backend, essentially. I think there's a lot of depth in this. But if you, depending on how fast you want to bring things up to, sometimes there's a lot of new components, and you might run a custom stack also, or you have specific requirements.
But short answer, I guess, is it will get you pretty far.
Very far.
Yeah, it's
like
a
Bryce said.
great point to start from.
Okay. And there's a question from Discord. Would you please talk about writing custom workers with KV routing and KV cache transfer?
Yeah, so I guess first of all, for KV routing, I guess that's certainly an area of our documentation that's lacking. We have examples for how to create custom workers, but at least as far as I know, none of them show like a full like sort of end-to-end integration with KV routing. I guess the big sort of thing needed for custom workers to support KV routing would be publishing those events over publishing those KV events over NATs. I'll go share my screen again. We have a
Give us 1 second. Are we sharing his screen?
Okay.
Cool.
Yeah, so we have this. So we have I'm just using the our TRTLM component as an example here, but we have this KV event publisher. We go spin up a thread that takes the LLM API, consumes those events from the LLM API and calls into our KV event publisher. This KV event publisher, it's implemented in Rust and binded into Python, and that should be everything you need for implementing a for I guess integrating your custom worker with KV events. I guess the second part of this for workers with custom KV transfer, that would ultimately be entirely, I guess, the responsibility of the implementation of that worker itself. Dynamo wouldn't really be directly involved in that. But I would definitely recommend taking a look at the Nixel Connect library in Dynamo. And it's sort of I guess I describe it as sort of a higher level wrapper on top of the existing Nixel bindings in Python. So it provides easy utilities for, like, for example, taking a torch tensor, registering it with Nixel and performing some transfer. Sort of I guess it abstracts away a lot of the a lot of the lower level details, I guess. So yeah, I'd say that for I guess anybody looking to implement a custom worker with KV transfer, at least going through Nixel, the Nixel Connect library would definitely be the sort of way to go there.
Awesome. So yeah, unfortunately, I think our time is running out. So we just wanted to thank you again for hosting the special edition of Dynamo live stream one more time to Base 10. Thank you, Bryce. Thank you, Michael. And we obviously were not able to get to all the questions, but we'll try to answer the questions offline if possible. So thank you again for tuning in, and we will have another one in 2 weeks. And so we would like to take some suggestions for topics, but please look out for the next edition of Dynamo live stream. Thank you so much. We'll see you next time.